This video concerns volumes of ellipsoids. We will use calculus techniques to find the volume inside an ellipsoid. We will see later that the equations of ellipsoids are given by equations like this: x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Let's define what an ellipsoid is. It's going to be a surface in 3 dimensions. An ellipsoid is going to be the graph of equations of this form: x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. And we will consider a being greater than 0, b being greater than 0, and c being greater than 0. We can assume this without loss of generality because we just have the squares of them here. So what does an ellipsoid look like? Well, it looks kind of like a flattened or stretched sphere. We will see several examples of this very quickly. Here we have the ellipsoid x squared divided by 1 squared plus y squared divided by 2 squared plus z squared divided by 4 squared equals 1. Here's the ellipse in 3-dimensional space. This is our x-axis going from, it looks like -7 to 7. For the y-axis, -7 to 7 perhaps. And on the z-axis, -7 to 7 also. This color scale here tells us the coordinate, the z-coordinate of a point on this surface. Let's rotate this surface around to see what's going on. If we go over this way, the extent of y values goes from -2 to 2, which matches what we have up here, y squared over 2 squared. If we rotate back this way so that we get the x-axis head on, right about there I guess, the extent of x values in the surface go from x equals -1 to 1. The z coordinates for points on the surface go from -4 to 4. So that gives us a pretty good example idea of what this ellipsoid looks like. Here we have the ellipsoid x squared over 2 squared plus y squared over 2 squared plus z squared over 4 squared equals 1. So basically in the x direction, which is along this axis, if we move this over, we can see, approximately at least, that this ellipse is somewhere between x equals -2 and x equals 2. And if we go this way to the y-axis, this ellipsoid is also between -2 and 2. And in the z direction, it goes from -4 to 4. This particular ellipsoid could be considered a volume of revolution. Here is, excuse me, here is another ellipsoid given by x squared divided by 4 squared plus y squared divided by 4 squared plus z squared divided by 2 squared equals 1. This x term and this y term both have denominators 4 squared, same denominator. Then we have 2 squared over this, under this z squared. In this case, we get an ellipsoid that looks like this, and we can see that it's not very high in the z direction, not very thick in the z direction. But if we rotate this around, if I can do it, this particular ellipsoid is also a solid of revolution, and that happened because these two coefficients of x squared and y squared were equal. Let's look at some cases involving ellipsoids. X squared over a squared plus y squared over b squared plus z squared over c squared equals 1. If c, a, and b are all different, we have which is called the general ellipsoid or the triaxial ellipsoid. The length of the three axes of the ellipsoid in the x direction, y direction, and z direction are all different. Suppose we look at the case where C is less than A or B, and A and B are equal. In that case, we get what's called an oblate ellipsoid of revolution, also called an oblate spheroid. In this case, C gives us basically information about the width in the z direction, and it's smaller than A and B. So the dimension, the length, or maybe the length of the axis in this direction, the z direction, is smaller than in the x and y directions. Down here, if C is greater than A, and A does equal B, then we get an ellipsoid that looks like this, that the length of this ellipsoid in the z direction is greater than in the x or y directions, and this is called a prolate ellipsoid of revolution, also called a prolate spheroid. What would happen if A, B, and C were all equal? Well, in that case, you would get a sphere. To find the volume of an ellipsoid, we're going to be integrating over a lot of ellipses. So the first thing we need to do is find the formula to calculate the area of an ellipse. We can do that by Calc 1 techniques. So our problem is to find the area inside the ellipse x squared over a squared plus y squared over b squared equals 1. So if we start with that equation, we can solve it easily for y squared, and we get y squared is b squared times the quantity 1 minus x squared over a squared. So that means that y is then plus or minus b times the square root of 1 minus x squared over a squared. If we use the plus sign here, we get this upper curve as being y equals b times that square root. We're assuming that a and b are positive here. So what we'll do is find the area under this part of the ellipse and above the x-axis, this region here that is shaded. So half the area of the ellipse, I'll call it a over 2, is just the integral of this, which is b times the integral from minus a to a of the square root of 1 minus x squared over a squared dx. Now, this requires a trig substitution. That's probably the easiest way to handle this. If you let u be a cosine x, then this fraction right here is going to be a square cosine square x divided by a squared. And so the stuff inside this square root becomes 1 minus the cosine squared of x, and the square root of that will give you the sine of x. I'll leave the rest of the details to you. But when you evaluate this integral, it turns out to be 1/2 times pi times a. And so half the area is b times 1/2 pi a. So the full area under the entire ellipse, top and bottom part, a is equal to pi times a times b. A is more or less half of this principal axis length. B is half of this secondary axis length. They kind of play the roles of radii in circles, but in this case we're looking at ellipses. So here's the situation that we're going to be looking at. We want to find the volume of the ellipsoid x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. And the intersection of that with the plane is shown here, a horizontal plane at a particular value of c. And what happens is we get the intersection of those two surfaces being an ellipse. We will see that this intersection is an ellipse. So what we can do is to find the volume of the ellipsoid, we will integrate the areas of these cross sections from minus c up to plus c, the values that z can take on. There are different types of ellipsoids, all given by this general formula. Let's consider A, B, and C in these denominators. If A, B, and C are all different, then we have what is called the general ellipsoid, or we could call it the triaxial ellipsoid. In this case, we're going to have three axes for this ellipsoid, all of different lengths. If two of the numbers, like A and B, are equal and greater than, let's say, C, then we get what's called an oblate ellipsoid of revolution, or just an oblate spheroid. In this particular case, we can get it by revolution, and we can use our calculus techniques for finding the volumes when you sweep a region around, let's say, an axis. If you have that A and B are equal and less than C, we have what is called a proloid ellipsoid. And if all of those A, B, and C are equal, then the ellipsoid turns out to be a sphere. So we can see that ellipsoids are kind of a generalization of spheres. But in this case, they can be stretched or contracted along various directions. Thank you for watching this video. What did we do? Well, we computed the area of an ellipse. We needed that to move on to ellipsoids. Then we computed the volume of the most general type of ellipsoid. The formula that we have covers all of the cases of ellipsoids. We didn't mention it earlier, but for the prolate and oblate spheroids, those volumes can be computed by using the formulas that you had in Calculus 1 for volumes of revolution. I hope you enjoyed this slideshow, and please stay tuned for more.